Okay, so we've seen that if you take a glucose molecule in the presence of oxygen, that it is, let me get my pen here, an exothermic reaction that you will form water and carbon dioxide. So that's exothermic. And if nothing else is done, you will lose that energy, that's potential energy in that glucose molecule, as heat and light in an explosion. Okay, but for life, we want to be able to use some of that energy anyways. So 39% to be able to do work, to grow and to reproduce. That process to get that energy out of the glucose molecule and use it is called cellular respiration. Okay, so here's our formula right here, our chemical equation. So we know that it takes a little bit of energy to break these bonds, and then a lot of energy comes out when these bonds are formed. So we want to use that energy. So instead of calling it an exothermic reaction, in biology we call it an endergonic reaction. No, sorry. Exothermic, exergonic. Exergonic. Okay, so instead of exothermic, in biology we call it exergonic, because instead of that energy being released as light, the energy is being used to do work. So exergonic. So the opposite chemical equation, the opposite reaction, so let's take 6 C carbon dioxides plus 6 water is going to give us 6 oxygen molecules and our glucose again. This opposite reaction is endergonic in biology. Before, in chemistry, it's called endothermic because it takes energy. The net energy is needed for this reaction to go. So it needs a lot of energy to break these bonds and a little bit of energy to form these bonds. So the net energy, there's a lot of energy needed in this equation, in this chemical equation. Okay. So some of the energy we've seen already. Energy is needed. An example of where energy is needed is to transport molecules across the cell membrane. And you can see right here that it's in the form of ATP. So in life, we can't actually use glucose itself for the energy of doing work inside the cell. Glucose is too stable of a molecule. So glucose needs to be transformed inside a cell to ATP. And an ATP is used to do work inside the cell. Okay, so what is ATP? So ATP is adenosine triphosphate. Let's spell that out. Adenosine triphosphate. And it is a nucleotide. So it is a monomer of a nucleic acid. So the parts of the ATP molecule, we've got adenine, which is a base, ribose, which is a sugar, and we've got 3 phosphate groups. So this is not as stable as a glucose molecule, but it can hold chemical energy, potential energy, long enough to be used inside the cell. So let's go back to this figure right here. So what happens is our ATP, here's our ATP molecule. What we're seeing in this cartoon is just the sugar right here, and then the 3 phosphate groups. So our ATP, actually let's go over this again. So remember that this is our cell membrane, and these are our phospholipid molecules, and then this is a protein inside the phospholipid molecule, and these proteins are pumping ions back and forth across the membrane. So we've got sodium ions and potassium ions. Remember, that's using it because it's going against the concentration gradient, that it's got to use energy, and it's using it in the form of ATP. So what happens is this ATP molecule hooks up to the protein, and a little bit of energy is needed to break off that ATP molecule. But then when this phosphate group right here forms a bond with this protein, a lot of energy is released. But the energy is transferred to the protein molecule, so that the protein molecule can actually change shape. So ATP is used to change the shape of the protein molecule. So the energy from that phosphate group bonding with the protein is used to change the shape of the protein to form the pump, right? Allowing the sodium ions out and then the potassium ions in. Okay, so to get from glucose, because that's what we eat when we eat sugar, we need to get to ATP. And that process is called That's the cellular respiration. To take that glucose molecule and transform it into usable energy, first in the form of ATP, and then to actually do work. So energy in the cell is needed to create the order that we were talking about. Is one of the one of the levels, or one of the characteristics of life, is order. So energy is needed to create this degree of order. So to actually move, like in this case right here, to move the ions back and forth across the cell membrane. So in the universe, or let's see, so the order there, let's see, okay, this is sort of like a double negative, so it's hard to say. The universe tends towards disorder. Okay, universe tends towards disorder. Disorder. Okay. This is called entropy. Okay, so entropy is measurement of disorder. Right? So the universe tends towards disorder. But life is order. It has to be ordered. So to be able to have that characteristic of life, of being ordered, it must use energy to create that order. Okay, and here is a cartoon that I really like. So I blame entropy, blame the tendency of the universe to become disordered. Okay, so I hope you found that interesting. Thank you very much.